Hello everyone, and thank you for attending today's webinar. On behalf of BIS Research, I'd like to welcome you all to our Emerging Battery Chemistries, Reimagining Electric Vehicles Beyond Conventional Lithium-ion Batteries webinar. This is Komal, Research Analyst at BIS Research, and I will be the moderator for today's webinar. BIS Research is a leading market intelligence research and advisory company that focuses on emerging trends and technologies which are likely to disrupt the dynamics of the market. The mission is to harness the potential of disruptive technologies to make the business thrive in today's digital age. For today's webinar, we have a steamed list of speakers. Firstly, we have Mr. Konstantin Solodovnikov, the Chief Executive Officer of Innolit. He has been a part of Innolit, a pioneering battery technology company since 2019. He has previously been a part of Rush Agro and Alrosa Company Limited. His focus at Innolit has been towards innovative battery technologies for affordable and powerful e-mobility. Next, we have Mr. Vani Dantam, the Chief Operating Officer for Energy Storage Technologies at Nextec Batteries Inc. Vani is a global executive with 40 plus years of experience in energy and technology transportation industry. Operated for 15 plus years at the VP level in sales, BD, operations, and engineering. Most recently managed a multi-gigawatt lithium-ion battery plant project in India. We also have Mr. Pranav Nagavekar. Pranav is a research engineer at University Paris-Saclay. His focus area have been towards synthesizing oxide-based and composite polymer solid-state electrolytes, test material with XRD, EIS, and testing solid-state batteries and conventional solid cell development in glove box. He is also a contributor for Volta Foundation, leading professional association dedicated to advancing battery ecosystem. Also, we have with us Mr. Dhruva Jyoti Narayan, Principal Analyst of Mobility Vertical at BIS Research. He's a keen electric vehicle enthusiast and has been tracking electric vehicle technologies for the past 4.5 years and has co-authored more than 70 strategy and market intelligence reports, custom studies, and client presentation in electric vehicle domain. I thank all the panelists for their gracious presence. So now let's discuss the agenda for today. We will start by highlighting the current trends and future potential for electric vehicle batteries, key development and industry players with the ecosystem, along with various investments and key minerals for electric vehicle batteries. In the next 45 minutes, we are all keen to learn from your experience about electric vehicle battery chemistries, and towards the end of the webinar, I will open the panel to the audience for any questions. I'd like to request everyone in the audience to kindly mute your phones during the webinar and type in the questions towards the end of the webinar. Any question that we are not able to answer today shall be reverted on a blog post or through email. Now let me open the panel for discussion and invite thoughts for discussion from Mr. Dhruva Jyoti Narayan. Dhruva, over to you.
Right. Thank you, Komal, for such a thoughtful introduction. I would like to also welcome our audience and our esteemed speakers. Thank you for your valuable presence. So I would like to start by giving a brief overview on the electric vehicle battery industry. So we have identified multiple push and pull factors within the industry that are influencing the market. If we talk about trends, so solid state battery has been one emerging technology trend that is seen as a potential replacement for current lithium-ion batteries. With properties like low flammability, faster charging, and moderately higher energy density, solid state batteries are receiving a lot of attention in both academia and industry. Another key industry is the Another key trend is the use of nickel-rich cathodes that has gained significant attention in recent years due to their potential to improve the performance and cost effectiveness of lithium-ion batteries. Research is still ongoing for finding high nickel cathodes with a combination of the best cyclability and best thermodynamic stability. Next, dry electrode manufacturing process has been key towards significantly advancing and lowering the battery cost. Not only does the dry electrode process eliminate the usage of toxic solvents like NMP in manufacturing, but it also reduces battery cost up to 50% through as has been published through various research papers. Companies like Volkswagen, Fuji, Lucas, TVS have already licensed this process in the United States. Next, emergence of lithium iron phosphate batteries, which are a type of lithium ion battery, are gaining increasing attention and popularity in recent years due to their unique properties and advantages, such as excellent safety performance. Also, some of the growth factors and drivers within this particular industry would include the increasing demand for electric vehicles and the reduction in cost of EV batteries, which we can also say are correlated. So, for example, the Department of Energy in the US, they have estimated that the cost of an electric vehicle lithium-ion battery pack has declined 89% from 2008 to 2022. So that itself is an indication how the cost has drastically decreased and the demand is supposed to increase because of the increased affordability of such vehicles. Also, increased investment in battery R&D in are along with advanced materials, cell designs, and manufacturing processes have further enhanced the industry. And various companies are collaborating with either startups or research institutes to further establish a very robust R&D path for their products. Followed by this, obviously, government policies and regulations are also a key driving factor. So government policies have been crucial, and in many countries, they have incentivized battery R&D, promoting manufacturing, creating market demand for electric vehicles, supporting charging infrastructure, and ensuring there is safety and environment compliance. So overall, ecosystem creation has been there, a push from various governments, and that has been one of the key growth factors. Now, when we talk about challenges, so within the challenges, procurement concerns over raw material remains a key challenge. So we all know that there are a lot of rare earth elements, lithium, cobalt, nickel, graphite, and other metals and minerals that are involved in the manufacturing of EV batteries. Now, we also know that many of these rare earth minerals are concentrated in few countries or regions, and that can create supply chain risk due to geopolitical tensions, trade disruptions, export restrictions, and any other factor. So based on our research, this has been one of the highest concern for most of the industry experts that we regularly talk to. Also, environmental concerns related to EV batteries. Um, for example, the extraction and processing of some raw materials for EV batteries includes a lot of deforestation, habitat destruction, water pollution, carbon emission. So this is also a concern, and obviously concerns over battery safety. So risks like thermal runaway, crash and impact safety, and charging safety of EV batteries remains a key challenge that is yet to be completely solved by the industry. When we talk about opportunities, various opportunities like sustainable and low carbon materials, along with various innovation in battery chemistries, which includes, of course, solid state batteries, lithium sulfur batteries, then other type of multivalent or flow batteries are there. And obviously, recycling and a circular economy, establishing such a economy within EV battery ecosystem is a key towards sustainable form for the overall ecosystem. So next slide, please, Komal. Right. Uh, right. So when we talk about the key players, so there are so many multiple players in the market. So some of the key players have been identified in this particular slide. So that includes Cattle, Panasonic, LG Chem, Toshiba, and then there are leading startups like Solid Power, QuantumScape, and S-Volt, and so on. So when we talk about developments, we saw a majority of development where either a company is investing in R&D and innovating with their products, or an electric vehicle OEM is collaborating with a battery manufacturer for specific battery demands for their models. So some of the key developments have been listed on the slide. For example, Samsung collaborated with Stellantis for their battery gigafactory about 1 year ago. And then for another example is that Cattle started with an upgraded version of their third generation cell to pack battery system called Quillen, which has already started and will be there for installation in in some upcoming EV models in China by the next quarter itself. So these are some of the key developments that we have observed. Next slide, please. Right. And also, when we talk about investments, as per my previous point, so a lot of companies are investing billions of dollars into this particular market. So we can see that companies like Volkswagen, Hyundai, Ford, all of them EV OEMs, they have invested a lot by either collaborating or establishing their own R&D centers for EV battery manufacturing technology. And when we look at the amount of minerals that are required for an average electric vehicle battery, so as per a research from Transport and Environment, so we can look at the various levels of different elements, different minerals, rare earth elements that are required to manufacture an electric vehicle battery. So the point is that there is a lot of activity ongoing. There are a lot of investments that are happening. Companies are making their move within this particular market, and they are trying to uh, go beyond the conventional lithium ion. They're trying to perfect their battery model as much as possible. And definitively, if you look at the trends as we saw on the slide, the market is going to boom at a tremendous rate, and any first mover advantage for any uh, you know uh, innovative battery chemistry beyond conventional lithium ion batteries are going to have a key advantage in the future. So talking about these type of batteries, which are not which are different from conventional lithium ion batteries. So I would next like to invite our first guest speaker, Mr. Constantine, to kindly share his views on this particular topic in our webinar.
Thank you. And before I start, I would like to thank BIS for inviting me and for the opportunity to present new technology that we've developed. If we can go to the next one, please. In the list, just a few words before I start is a startup. It's a standard one, and the next, please. It's a startup from Switzerland and Germany. We have a lab in Brussels, south from Frankfurt, and the team has been working in the area of electrolyte research since more than 20 years. We're 85 people team and develop a new technology which is different from conventional lithium-ion. It's a liquid electrolyte based, but inorganic liquid electrolyte. And in the following few slides, I will show what we've managed to achieve. And it's an interesting technology, in our opinion, promising technology that helps to solve some of the major challenges in the industry and potentially also go beyond conventional lithium-ion. We have 400 patents comparable to QuantumScape, Prologium, or Solid Power. And this technology fully belongs to us. And currently, we're going into industrialization stage. Next one, please. The major challenge which we're trying to solve is certainly the cost of electric vehicles versus ICE engine. Despite of the prospects of further electrification and the increase of electric vehicles, the number of electric vehicles on the roads in the next 10 to 15 years, what you can see on the left side, the fundamental challenge remains the same. It is still more expensive to produce electric vehicle than an ICE engine car with similar performance. And one of the ways to solve this price difference is to reduce cost of battery cells inside and potentially also simultaneously increase their performance. This is what we're doing. And next one. Next slide, please. Yes. We see on this way of closing the bridge between ICE and electric vehicle, we see 6 major challenges. One, and the most important one from the economics point of view, is cost. Second, energy density, temperature performance, fast charge capability, safety, and of course, recyclability, which is gaining its importance basically every month, every year. Next one. Our electrolyte has a special high stability to the voltages of up to 5 volts. For those of you who are familiar with electrochemistry, maybe it's not a very informative slide. For others, maybe just to explain in a few words how inorganic electrolyte works. The conventional one usually is cycled up to 4.2 volts, and that is the limitation. Beyond this voltage, electrolyte becomes not stable. With 4.2 volts in the cell, conventional or existing battery manufacturer would get 100% of capacity, a number that would be accessible for them with the set cathode anode material. Our electrolyte is stable to higher voltages, as I've mentioned, up to 5 volt. So, for example, with NMC 811, we usually go to 4.6, and this is what is shown with arrow A. Going from 4.2 up to 4.6 volts, and then continuing along the charge and discharge curve, you can see on the x-axis that we get additional capacity of 20 to 25%. And this is exactly thanks to high voltage stability. And with high voltage stability, we can utilize almost 100% of lithium inside of cathode material. And using this full potential of cathode material, we increase capacity of the cell, and for the same capacity, we reduce quantity of cathode in a cell. And we can go even beyond 4.6, and that would be case B, green arrows on this chart. And then we can get access to completely new materials, which are developed but currently not produced in mass production, simply because there are no end users for those materials. And there is a quote, it's a public quote, it was made in Reuters last year by Panasonic, where they stated that someone who can get to 4.5 or 4.6 volts and cycle battery cells stable would advance electrification beyond what we see today. So hopefully we're contributing to this process with our technology. If we can go to the next one, please. On the left side, you can see what happens with conventional organic electrolyte when it's cycled to high voltages. And I would remind you that high voltages are required in order to get access to more of available lithium on the cathode side. With high voltage cathode in conventional electrolyte gets into reaction with it, oxygen is released, and it leads to decomposition of electrolyte and formation of very toxic acid HF. And then HF attacks backwards cathode material, and it also passivates on the current collector, and at the end we have very fast degradation of the cell, and that's the reason conventional lithium-ion cannot be cycled at high voltages. Basically, cells cannot live any reasonable cycle life. With our electrolyte on the right side, you can see that it doesn't happen. There is no formation of HF, and it makes the system stable at high voltages. We can go to the next one, please. Can we go to the next one, please? Yes, our electrolyte, it's shown in green in the middle, compared to the versus conventional organic electrolyte on the left side to it. Has, besides voltage stability, also very high conductivity. You can see on this chart that versus 6 to 12 millisiemens for conventional, we have almost 4 times more. And with this higher conductivity, we bring also power capability. There is absolutely no limitation on the side of electrolyte for development of power capability and the higher C rates in the cell. Also, electrolyte is stable to high temperatures. It's not flammable at all. It's inorganic, and there is no flash point for it. Unlike, of course, organic electrolytes, on the low temperature side, we can get access to more than 70% of available capacity, even at the temperatures as low as minus 40 degrees Celsius, and electrolyte is still liquid, and there is conductivity in the system at minus 60. Can be very useful for many different applications, especially in Northern Hemisphere. And last but not least, with organic electrolytes today, one can work with commercially available materials. And as I've mentioned earlier, not with the new materials that had been developed, and they require higher voltages, like many of the combinations with manganese, where content of nickel, that is expensive and also relatively hard to source. Replacement of nickel with manganese is one of the future opportunities in the industry. There one needs higher voltage in the system, and conventional electrolyte is an obstacle. We can move to the next one, please. How it works. On the first line, you can see that conventional system usually utilizes about 80% of available lithium on the cathode side. And in case A, our electrolyte get access to almost 100%. That's how we increase utilization of available cathode material, and we increase energy density in the cell, and plus we add performance that comes with our electrolyte. And below, what I've mentioned earlier, use of new materials, that is case B that we've shown in the previous slides, versus some of the solid state technologies. And I don't want to maybe offend any of the companies that are developing it. They are doing a great job, all of them. We believe that on average, still there is some room for improvement in the solid state development. And really beyond conventional lithium-ion, the industry in general believes solid state is a savior. We see it as a technology that can potentially come at a later stage, but when it comes, it would still have several challenges, and one of them is manufacturability, and the cost per kilowatt hour will be the second one, which comes close with the first, but also is linked to the bill of material in production of solid state batteries. Let's go to the next one, please. Yes. Our current battery cell is made in 21700 format. We have high utilization of cathode, and that's why we need 20% less metal inside of the cell, which brings its cost down roughly by 10%, because cathode is approximately 50% of cost of a battery cell. Energy density is 15 to 20% higher than of the conventional cells in the market, 300 watt-hours per kilogram, and that is with 100% charge and discharge, full capacity available. Safety is increased, as I've mentioned in one of the first slides. There is no flash point. Electrolyte is not flammable. When a cell goes into thermal runaway for any negative reason, normally there are two sources of energy. One of them comes from lithium and other materials like separator, and another one is approximately 50% is electrolyte. In our case, electrolyte does not release any energy, and 40 to 50% reduction in the energy release means fire propagation is reduced down to almost zero. We've tested it, and it's a very interesting differentiation with conventional lithium-ion technologies. Then on the lower temperature performance, I've mentioned already, the cell can be discharged at -40 and charged at -20, and approximately 80% of capacity would be still available. Electrolyte is fully recyclable, and that is also a strong differentiation with organic electrolytes, where normally electrolyte salts cannot be recovered during recycling process. On the fast charge, 15 minutes is just an average which is required for electric vehicle applications, but we've managed to achieve significantly higher rates of 7C, 8C, up to 10C, which would be 5 minutes, 6, 7 minutes of charge and discharge time. Next one, please. Technology which we've developed with this liquid electrolyte is fully compatible with the existing materials, supply chains, and equipment used for production. The system is also compatible with the use of silicon. So if there is a need to reduce quantity of anode material and further increase energy density with some compromise and trade-off on the cost, because silicon adds cost to the cell, it would be possible. We're working on this combination as well. So upper part of the table shows existing technologies of today. We see a number of challenges in this respect for solid-state technologies, but some of the companies managed to solve partially those challenges. I don't want to say it's completely impossible. In the future, which is lower part of the table, conventional lithium-ion cannot really improve its performance. There are limitations of voltage and efficiency in general. And this is where high voltage would play a significant role. And using liquid electrolyte that we've developed, we call our technology I-state. It is possible even to develop in standard cell formats lithium metal technologies and chemistry. We've done already first tests, and in cylindrical format achieved 400 watt-hours per kilogram. And currently we're working on increasing cycle life of those batteries. Please go to the next one. Three pillars of cost advantage versus conventional lithium-ion. Number one is cathode use. I've already mentioned enough about it. Overall higher capacity in the same cell due to high utilization of lithium on cathode side, brings share of other raw materials per kilowatt hour down. And there is the third pillar of cost improvement, and it's in production process. Our electrolyte is not sensitive to humidity in the production environment. So conditioning of production process, production area would be less strict. Currently, we are not using, for example, any dry room environment for production of our sample cells. And in any factory, that's a big part of the cost. We've seen in the introduction presentation dry electrode production as one of the ways to reduce capex and reduce manufacturing cost, lower higher humidity tolerance and low requirement in this respect would be in addition that can improve further manufacturing cost and help to bring cost of electric vehicles closer to ICE engine. Next one, please. What I haven't mentioned yet is ESG requirements, use of or high utilization of cathode and use of fewer metals per kilowatt hour in the battery cell obviously contributes significantly to lowering CO2 footprint. That is a big achievement that can be achieved with our technology. And the recyclability of electrolyte salt due to the solvent which we're using, our solvent is inorganic, that makes electrolyte inorganic as well. And it's a waste material of fossil fuel production, oil, gas, coal, metal refineries, they all emit a lot of SO2. We use SO2 as a solvent, and it can be easily captured during recycling process. So salt itself can be recycled and solvent can be captured as well. As total, all the materials in the cell taken, percentage of recoverable useful materials, including valuable metals, will be higher compared to conventional lithium-ion. Let's go to the next one, please. Very briefly, the first technology which is currently introduced to the market with this new electrolyte, liquid inorganic electrolyte that we call I-State, brings roughly 20% additional energy density compared to the existing technologies in the market. And with the next technologies that we're currently developing, and this is really a possibility with this electrolyte, it's not one time solution, like one combination of materials that only works. There are several of them, and we can see them on the next slide. Here, the dashed line is theoretical maximum capacity and energy density that is achievable with conventional lithium-ion. So there are barriers. There is a necessity to develop new technologies in order to further electrification in the world. We can go to the next one, please. These are chemistries which can be developed based on this liquid inorganic electrolyte, starting from manganese-containing ones that would bring higher cycle life and lower cost, like LNMOR and manganese-rich NMC, LMR. Also, sodium can work with this electrolyte, and LFMP as an alternative to LFP. Manganese in this LFP as an addition would enable higher voltage that can be applied to the cell and higher energy density, which is currently a limitation for LFP cells. On the second half of this chart, with lithium metal, high nickel, and high nickel with silicon cells, and NMC and graphite, what we're using in our entry-level technology, we achieve high energy and also competitive cycle life and C-rate capability. All of the technologies can be used for different kinds of e-mobility, not only for electric vehicles, but also for airspace, aviation, urban air mobility, eVTOLs, industrial applications, etc. And this electrolyte can be used in cylindrical formats, can be used in prismatic formats as well. Next one, please. I think yes, that's it. It's probably not the most modest slide in our deck. Apologies for it, but it's true. In terms of differentiation with conventional lithium-ion, our team perhaps is one of the few, if not the only one, that has differentiated technology with a number of advantages in terms of performance, plus lower cost and plus recyclability. So this liquid inorganic electrolyte as a possible way to address challenges of the industry is something which is worth looking at, and we're currently introducing it to the market and sending sample cells making tests with interested customers. So please, if you have any questions after this podcast, we'll be happy to answer them in any form. Reach out directly. You can find our contacts also on the website. If I cannot answer them now, of course.
Thank you for your insight, Konstantin. Now, I'd like to invite Mr. Vani Dantam to present his views in today's webinar.
Good day, everybody. Can everybody hear me okay? Next one, please. I'm always fascinated by history. How much energy the world is going to need as the civilization reaches different stages. This is the way Russian astrophysicist Nikolai Kardashev considered different energy consumption models and how the civilization is going to become. Type 1 civilization, he calls it out at 10 to the power of 4 terawatts of energy generation. 10 to the power of 4, you put that in perspective to where we are. In 2021, our energy production across the globe was only 11.05 terawatts. So, from Kardashev's perspective, we're not even in a type 1 civilization. And when you go type 1 to type 2 to type 3, each time you are exceeding by 10 to the power of 10 additional terawatts. That is 10 billion more terawatts each time you go 10 billion times. So imagine that. And this is when you start farming energy from astronomical sources. For example, you can build Dyson spheres. This is what British theoretical physicists developed a model. They're called Dyson spheres. So you build around a star a network around that can capture the star's energy. So you're actually doing farming of energy from universe, different galaxies and whatnot. I mean, I cannot even imagine. And after Kardashev got done with this, the science fiction writers even extended it all the way to type 7. So imagine how much energy you would be needing if you were to go to type 7. I can't even imagine type 1 right now because we are so low compared to, Kardashev's perspective of type 1. So out of this 11.05 terawatts of energy production we had in 2021, fossil fuels accounted for 4.4 terawatts and it's been going down. And renewables and energy storage systems accounted for 3.2, and that has been going up steadily. So it just puts a different perspective in our minds where we have been and where we are heading. Next slide, please. A lot of us don't know when lithium-ion batteries were invented. There's an American physical chemist named Gilbert Newton Lewis invented the lithium-ion batteries. He's considered the father of lithium-ion batteries in 1912. Imagine, 1912. And he holds the record of the most nominated person for Nobel Prize. He was nominated 41 times for Nobel Prize. He never won. 1912. And how long did it take us to commercialize the lithium-ion technology? Next slide, please. In 1976, the British chemist Michael Stanley Whittingham, who is now a professor at the State University of New York in Binghamton, he patented the first viable lithium-based battery. So from 1912 to 1976, that is 64 years after the battery was invented. That's how many years it took us to commercialize. And for that, in 2019, Professor Whittingham and Professor John Bannister Goodenough from University of Texas in Austin and Akira Yoshino from Japan, all three won Nobel Prize in 2019 in chemistry for their contributions to commercializing lithium-ion technology. So that just puts a different perspective. And next slide, please. Next-tech batteries. What are the objectives? In terms of any kind of energy storage technology. Obviously, we want lower cost. We're not looking at dollars per kilowatt hour anymore. It is dollars per kilowatt hour per year. So if you bring the cost down and the life goes down more than what the cost is going down by, not worth it. So you have to look at normalizing both from dollars per kilowatt hour basis and also dollars per year basis. I had worked for Toshiba Japan as a VP of Sales and Business Development many years ago, and Toshiba specializes in lithium titanate technology. And theoretically speaking, these batteries had the longest life of any batteries that I have worked with in my career. The theoretical life of these batteries for 47 years. Imagine that, 27 to 30,000 cycles of life at 80% depth of discharge. But the battery was so expensive, customers chose these batteries only for highly specialized applications. And again, the technology was evolving so fast, even though the battery had phenomenal performance, customers were still very weary because of the high cost. You're looking at $500 plus per kilowatt hour. So when you normalize dollars per kilowatt hour per year, you get a different perspective. Obviously, you want higher performance. This is both gravimetric energy density and volumetric energy densities and higher life. Faster rechargeability, how fast you can recharge the battery, and superior safety. We see and hear about batteries catching fire and cars burning up. Even residential energy systems, there have been cases of fires. So you have to make sure the battery is going to be very safe. And then the next one is lower weight and volume. How much can you shrink the battery? Because if you look at the car size, a small EV weighs actually more than a mid-sized gasoline-powered car. And how does this impact us? If you look at parking garages in big cities, they were all planned for gasoline engine, IC engine cars. And if you park more than 20% of the vehicles on a parking garage floor, EVs, the garage may collapse. Imagine that. We haven't thought about it yet. If you go to any of the big cities in the world, you have multi-story garages, and they're not designed for EVs. So this is something we have to think through. And this is why we have to continue our work on reducing the weight of the battery pack. A full-size Tesla weighs almost 1,500 to 2,000 pounds more than a full-size IC car. So it's a problem that we have to deal with. Lower carbon footprint. This is another thing we all fight for. We don't realize how much earth we dig up to build a single battery pack. To build a 65 kilowatt hour to 100 kilowatt hour Tesla battery pack, you have to dig up anywhere between 50,000 tons to 75,000 tons of earth. Can you imagine how much carbon footprint you're leaving? And not only that, you are using cobalt and nickel. These are all high melting point metals. So to produce these metals, how much carbon footprint you're leaving? To make a Tesla carbon neutral, you have to drive that car by more than 90,000 miles. People don't know that. Just because you buy an electric car, you bought an electric car doesn't mean you're becoming carbon neutral. So all of these things need to be thought through. So that gives us, again, regionally available and sustainable materials, environmentally friendly materials. Next slide, please. The development of the next generation batteries, what is it being driven by? New and environmentally favorable chemistries, less capex intensive and quicker electrode pasting, less capex intensive cell assemblies, shorter formation cycles, application-based battery management systems and module designs, application-based electrode metrics. All of these need to be brought together to build our next generation batteries. Next slide, please. This is where we are, and this is where we're heading to. This particular forecast was put together by one of the consultants in the energy industry. And this was put together a couple of years ago. That 180 billion total addressable market has already grown to 225 billion. So this is what we're looking at. And we are today between 50 and 70 billion. And you're looking at in the next 2 years going to 125 billion. And by 2030, you're looking at probably 200 to 225 billion. Next slide, please. Next Tech, who are we? Our company was founded in 2016. We're based out of Carson City, Nevada. And our goal is to become the industry leader of lithium sulfur batteries and solid state batteries using lithium sulfur technology. We are the exclusive licensee of Professor Elton Kern's inventions from University of California, Berkeley lab. And we have our own portfolio of patents, trade secrets, and manufacturing expertise. We've been at it now for 7 years. And we have a multidisciplinary team of 33 engineers and technicians, including 4 PhDs and working in the US. And we have gained deep expertise in material synthesis, design and prototyping, operations, and battery cells. To date, we have invested over $20 million. We plan to invest another 30 million because we are getting ready to build our pilot plant. And we also are now totally UN certified. So all of the cells that we produce with lithium sulfur chemistry have been UN certified. And that is something that none of the other LIS manufacturing companies can declare. Next slide, please. Our target markets, obviously, electrification of transportation, electrification of ag machines, drones, and electric VTOLs. And then replacement of current lead acid batteries. This is very important. You cannot do replacement of current lead acid batteries with LFP or NMC chemistries because the cell voltage is so different. Putting a module together is very much a pain in the neck. With regards to lithium sulfur, the cell voltage of lithium sulfur is identical to that of lead acid battery cell voltage, 2.1 volt. That means I can put 6 cells in series and you have a lead acid battery replacement. But the size will go down by 50 to 60%, and the weight will go down by 70%. Imagine that. And obviously electrification of industrial machines and for grid storage. Approach. We are the only company, lithium sulfur battery company, that has produced cells with more than 400 watt hours per kilogram gravimetric density and more than 400 watt hours per liter volumetric density. And our 2026 target is $60 per kilowatt hour. I think, this is me personally saying that number can be brought down even more if I were to go to an organic sulfur cathode material. Today we have to use excess lithium to balance and to provide for polysulfide formations. But if I can mitigate and eliminate the polysulfide formation, I can reduce the amount of lithium I'm using. And also, depending on how we synthesize the sulfur in the cathode active material, we may be able to reduce that $60 by another 1/4. So you're potentially looking at, $45 to $50 easily, depending on how the research progresses. Already mentioned, we have completed the UN 38.3 certification of our current cell designs, and our goal right now is to build a pilot plant in the next 18 months to increase our production capacity and produce additional cell designs. We will be supplying cells to BIS certification in the next few days. So that's another thing that we're looking at. Value proposition obviously is lower cost with simplified manufacturing process, significant weight advantage, and improved safety profile with better performance. Next slide, please. Here is the technology. Manufacturing. The manufacturing of the cathodes is very similar to lithium-ion batteries, so you can use off-the-shelf manufacturing equipment while we are cooking up different kinds of manufacturing technologies. Anode is pure lithium metal, so you don't need any anode pasting. It's a lithium foil. And so you can go through what we call Z-stack assembly. So the assembly of the cells become very, much easier than the standard cells. Cathode, you have mainly sulfur and graphene. So the cathode is where, it's very light compared to the traditional cathodes. Obviously, anode, pure lithium foil, very light again. So if you look at it, there is no oxygen in cathode. It's sulfur and graphene. So when the battery becomes hot and the separator melts, you short the battery out, the battery will not go into thermal runaway because there is no self-sustaining oxygen inside the cell. Electrolyte, we use standard ether-based electrolytes. We also developed additives to the electrolyte to mitigate polysulfide shuttle and polysulfide formation. We have looked at partners for both JVs and for licensing arrangements, and we are actively working with multiple companies in India right now to develop initial business models, either as a licensing model or as JV model. Next slide, please. Here are the traditional issues with lithium sulfur system. You have dendrite formation, which basically pokes holes through separator and shorts the battery out. And we are developing and have developed electrolyte additives, looking at different electrolytes, and also adjusted the charge profile dramatically to reduce dendrite formation. And we are looking at pulse charging to break up any dendrites when they form initially. We talked about polysulfide shuttle, polysulfide formation and conversion. Again, the electrolyte additives that we have developed reduces the polysulfide formation and shuttle. And the insulation of sulfides, this is high sulfides and the traditional lithium sulfides. These are basically, this is the way we have designed our cathode active material it increases the conductivity, and so you reduce the insulation issues, and also increases the performance significantly. We have tested our batteries up to 10C. You can continuously discharge them or recharge them at 3C, no issues. And you can discharge the batteries at 10C for up to 1 minute. And this is what you need, especially in an application like a two-wheeler, where the acceleration and initial acceleration is a definite requirement. The 10C capability helps you quite a bit. Next slide, please. You're looking at here a comparison of traditional lithium-ion battery manufacturing versus Nextech's lithium sulfur. You can see cathode, it's much simpler. We use water in our slurry making. And this is another area that you can improve quite a bit because sulfur being so light, it is amenable for dry pasting, especially if you use something like, some electrostatic pasting, because you can electrostatically charge the substrate foil and apply the cathode active material, and then immediately anneal the material by rolling it through hot rollers. So this is something that we're thinking through that might reduce the cost of cathode line even more compared to where we are today. And obviously anode, no pasting, so no capex is required. And traditional electrode manufacturing, you go over 50 different steps. And compared to that, our number of steps have been brought down to less than 25, actually 22 to 23, that's what we have. And also the next thing where you save quite a bit of money is the traditional lithium-ion cells. They take anywhere between 1 to 2 weeks for formation, depending on the type of chemistry you use and type of formation cycles you deploy. And in our case, the entire process takes 2 days. That means the in-process inventory is going to be significantly less. That means the plant square footage you have is going to be substantially less. So when you combine no pasting requirements for anodes and formation cycle going down to 2 days, you reduce the plant size by almost 40%. So that means your break-even point for lithium sulfur goes down significantly, both from lower bill of materials, lower capex, smaller plant. You're probably looking at 800 megawatt hours to 1 gigawatt hour commercial volume to break even. Next slide, please. Managing the supply chain, traditional lithium-ion versus lithium sulfur. We need lithium metal foil. Depending on how you address the chemistry, as I was mentioning, if you can deploy organic the sulfur active material instead of mechanical mixing of sulfur and graphene, and then tie down sulfur better than where we are today, you would be able to reduce lithium metal consumption. We do not use any heavy metals. So the battery in general, the chemistry in general is a lot more sustainable and environmentally friendly. And no toxic solvents when you are mixing the active material. We use water. Again, we do not require any conflict metals from Republic of Congo or Russia or Indonesia. Readily available US sourced minerals. Even from Indian perspective, the materials can be sourced within the country. And the electrolyte, we have a proprietary formula. That's one of our trade secrets. Next slide, please. Can we have the next slide, please?
Is the slide visible?
No, it's not. I haven't seen it. So. I'm still, I'm still on managing the supply chain slide, Komal. I don't know if you need to back up and advance again. There we go. CapEx. All right, this is the CapEx that we have developed in terms of different areas. The total gigafactory cost for a 2.5 gigawatt hour, we estimated at 73 million. And where do these $73 million go, and how does it compare compared to the traditional lithium-ion battery? As I was mentioning, 40% less. The number is actually 36% less than traditional lithium-ion batteries. So you see where the total cost goes on a percentage basis. So this is a major advantage, especially for developing countries like India, where you don't have to spend enormous capex. You can actually put smaller regional factories and take advantage of this kind of technology. Next slide, please. Here it is on a gigawatt hour basis. Where are we compared to the rest of the technologies? A lot of these numbers are older numbers, like LG, Northvolt, Panasonic. They built their factories quite a few years ago. So if they were to rebuild the factories, the cost numbers might differ today, much lower. The most recent numbers that have been published with lower capex are like Freyr. Freyr uses 24M technology. I worked with 24M for many years before I joined Nextech, so that's also pretty low. But Nextech is basically, at half the cost of what other, current technologies are looking at. So this number can be brought down even more if I were to redesign my pasting of cathode active material. So lot more, even though we are very low, the lowest of probably many of the technologies in terms of capex numbers, that number still can be brought down, by another easily 15 to 20%. So the break-even point we believe is 800 megawatt hours to 1.2 gigawatt hours, depending on the location of the plant. That number is about half of what it is for traditional lithium-ion batteries. Next slide, please. Thank you.
Hello. Am I audible?
Yeah, Pranav. So thanks,
Yeah,
Vani,
Yeah.
for the views. Now, Pranav, you can start.
Yeah, sure. So we have seen two amazing presentations from Konstantin and Vani. One about the liquid electrolyte, a new development into the electrolyte of the conventional cells, and also on the lithium sulfur batteries. So I'll be just looking into the solid state batteries, but it will be more general introduction to solid state batteries. Next slide, please. Can you move to the next slide? Yeah. So we have already seen in the last two presentations that why do we need a new battery technology? Konstantin and Vani has clearly identified that with specific numbers, that where we stand with the current battery technology and where we want to move up to reach a certain energy level. And that's the main motivation to find new battery technologies, and that's what we are currently discussing. And one of the options here is to look into the solid state batteries. Can you move to the next slide? So in the last slide, we saw a mention on dendrites. I think it was Vani who mentioned it. So just looking more into it from pictorial perspective, if you assume this is an anode and this is the cathode side, and we have in the traditional cells a separator in between and liquid electrolyte. So eventually, over the period of time, what is happening is the lithium metal, it starts growing out in a root-like structure like this, and eventually it penetrates the separator, and then it travels further ahead and it touches the cathode part. And when this path is connected, this is basically an internal short circuit, and this may lead to cell failures, and also in some cases thermal runaways, or where the cell catches fire. So this is one of the major challenge, one of the major troubles we have when we try to look into new forms of anodes which are having more energy densities, because the pure lithium metal anodes or silicon based anodes, they have the capacity to expand rapidly, and when we are using them with the current liquid electrolytes, they are not able to suppress this dendrite formation. And if this dendrite formation is not stopped, it's really a difficult challenge to replace the existing anodes with a pure lithium anode, or with a silicon based anode, or any other high energy dense anode. Next slide. So what the previous thing results into, I said, is basically thermal runaway, but it could be a result of either of the situations, where it could be because of some mechanical abuse happening to the cells, or some electrical abuse. It could be something like a dendritic short, you can mention here, or it could be a thermal abuse because the environment of the battery pack has gotten hot, and eventually it leads to an escalated set of temperature in every scale. And higher temperatures gives rise to higher rate of reactions, and then it leads to eventually thermal runaway as well. So it could be because of some mechanical abuse like a puncture, or it could be some electrical abuse or thermal abuse. Either way, it's going to lead into a thermal runaway. In some cases, there can be a short circuit, but it may not be eventually catching fire in some battery chemistries. Next slide. Okay. So what we are looking into is, we are trying to solve the challenge on multiple stages. We are trying to solve problems of the dendrite growth. We're trying to challenge the safety issue, where we don't want the batteries to go into thermal runaway. At the same time, we also want a very high amount of energy density, and we want low cost on the batteries. We also want very less charging times. So these are all collective combining factors that are motivating us to move to new battery forms. This is basically a solid state battery with respect to liquid electrolyte, and there's not much difference. So you can see we have a positive electrode in both the cases, we have a negative electrode, and in between, for a solid state battery, we have a solid electrolyte. And for a liquid electrolyte, there's a separator in between which separates the two forms. In the solid state electrolyte, we don't need an additional separate a new element to put into. We don't need a separator. Basically, the electrolyte itself is acting as a separator between the two parts, between the two electrodes. And as seen here, so the thing that we are looking into is, if we are replacing this with a solid electrolyte, we are possibly having a lot of advantages that we are going to look into. But before that, how does this work? What is the difference in the working mechanism of these two batteries? Basically, for the liquid electrolyte, the ions, they're traveling through the liquid. They are basically swimming from one electrode to the other electrode during the charging and discharging cycles. But in solid state, the ions, they cannot travel in the same way. So in this solid electrolytes, they are traveling through something called as diffusion. So I believe in 11th, 12th standard chemistry, we have studied about diffusion. Can we go to the next slide? Yeah, so basically, in diffusion, we are making the use of vacancies or defects into an element's properties, and the ions, they are just pushing the next location, and they're trying to move in a path that has been created due to some defects into the element. In this case, in solid state battery, what we do is to move the ions from one end to other end. There's an example here. So let's assume that we have a structure of lithium and chloride. And what we did was, we took out some lithium from the spots, and instead of that, we replaced those with this magnesium. And we know the charge on lithium is a single positive charge, and magnesium has two positive charges. So to add two magnesium, I'll have to remove two lithium, and so this has eventually created two vacant spots. Now these two vacant spots are basically can be shifted to. So the lithium on the left side can move to the vacant spot, and whatever, when the one lithium moves to the other part, there's a vacancy created behind. So there's a path for the next lithium to move to that spot and so on. So if we have such vacant defect path, it can travel from one end to other end. And this is the way it's supposed to travel from anode to cathode and cathode to anode. So this is basically how it's going to work, how the transfer of ions is going to work in case of solid state batteries. Can we move to the next slide? So we saw how the ions are going to move, how it's going to work, but why do the solid state batteries are having more energy density? And again, this we have also seen in previous sessions by other people, where they mentioned the energy density difference. So if we are using a lithium metal, it has almost 10 times the capacity that of the graphite that's currently being used. So if you compare the anodes of the graphite anodes and lithium metal anodes, you can see the difference in the size in the cell level itself. So it's a very small. So we are able to reduce the thickness on the cell level if we are comparing the same sizes. Okay, of course, in case of cathode, there is no change because both of them were using the same cathode material. That again depends on if you are trying to develop new cathode, but that's a different thing. As of now, from anode's perspective, we are able to use lithium metal anode, and this is the reason I mentioned the dendrite challenge in the first slide, because we could have possibly used lithium metal anode for the conventional cell as well. In fact, when I'm developing cells in lab, when I'm testing cells on even on conventional cells, I use lithium metal for conventional cells as well. But the problem is the liquid electrolyte and the separator. It's not strong enough to suppress the dendrites after a few cycles. So once I charge and discharge the cell for n number of cycles, it's going to start forming the dendrites and it's going to have an internal short circuit. But with the solid electrolyte, there is a possibility that they may be able to suppress the dendrite formation at a higher level than the conventional cells. Next slide. So coming back to the energy density part, so we are able to have more energy density on the cell because now we have the possibility of using a high energy dense lithium metal. So solid state battery, when we say that they're more energy dense, basically it's just that here we have the possibility of using lithium metal. That's it. So the electrolyte itself or the technology itself is not improving the energy density directly. It's basically the solid state electrolyte is allowing us to use a high energy dense anode, which in turn increases the energy density of the cells. But this stacks up because now we have energy density on the cell level and then on the module level and on the pack level. And one more advantage here is that the solid state batteries have a wide temperature range, wide operational temperature range, and even at higher temperatures, they allow the fast transfer of ions, but they do not have any possible failures or possible defects the same way as the conventional cells have. Basically, that means we may potentially be able to avoid any high thermal management system. We may be able to work the batteries without or with less amount of thermal management system. That basically gives us more space again to improve the energy density on the whole pack level, not on the cell level, but more again on the pack level. So we have improved the energy density on the cell level, then we have improved the energy density again on the pack level. So that's why we are going to have an overall high energy density on these battery packs. Next slide. Yeah, so there are a lot of queries or a lot of questions on the safety of these batteries, and while they are safe in one way, they may or may not be safe in other ways. So here's this one, there's a video which was a study made by University of California, San Diego, and there they had made the solid state cell and they were cutting it while the cell is operational. And you can see even after cutting the cell keeps on operating. It's been cut in a direction in which all the layers are intact, although the safety is still not completely, it's not completely safe yet, because here the problem is we have replaced the graphite with lithium and we have like more amount of lithium in your battery pack. Again, lithium is highly reactive to atmosphere, and any possible way which if the battery pack is not sealed properly or if any other external factors interfere, it may be not safe. So the safety part is still a question where the study is still going on, but it's definitely safer in one particular way, where you can see if you penetrate a regular lithium-ion conventional battery with a nail, it's called a nail penetration test, where a nail is passed through the battery pack, it immediately creates short circuit and it explodes. Or if you're trying to cut the liquid electrolyte battery, it's going to have a failure, immediate failure. But in this case, we can say it's at least safe in one particular domain, and the other studies are still being carried out. Can we move to the next slide? So we have seen one of the challenge, that is energy density, and how solid state batteries are having high energy densities. The next challenge we have seen was safety, which is still a little bit in the doubt, but still it still has its own advantages in terms of safety, as we saw from the photos. And now we move to the charging part. One of the problems that we face is charging limitations. The ions which are moving from anode to cathode and cathode to anode, basically how fast the ions can travel, and they can be intercalated into the anode side. That is one of the challenge which restricts the charging speed for us. If you're trying to charge it too fast, just imagine it. I know a professor who described it in a way where it's like a parking lot. If where the vehicles are coming through, paying through, and they're going and parking the vehicles, and at the same time, some of the people are taking their vehicles out and going out. They're showing their ticket and they're going out. But if too many vehicles come together at the same time, they cannot enter the parking lot at the same time. It's also similar to like an analogy for the bridge. If you're traveling on a bridge and the whole road and you enter the bridge part, there's a lot more traffic because the number of vehicles that can pass through that bridge is less, it's limited. It's somewhat similar to here also. Like the number of ions that can pass through and they can be intercalated into the anode at a given time is limited. And this is going to limit your overall capacity of how much ions you can pass and how fast you can charge your batteries. And this challenge is again a lot better theoretically for solid state batteries. And we have also seen some studies, because this is the study chart from QuantumScapes, which they had released, where they were able to charge it in under 15 minutes. But then again, even for some of the conventional cells, we have seen that there has been a lot of improvements in the charging times, and we are seeing that the conventional cells are also coming close to fast charging. But definitely, when you're comparing the two, solid state batteries have a higher potential of getting charged at fast series, and like having charging times reduced under 15 minutes or even 10 minutes or better than 10 minutes. Next slide. Okay, so we have seen the high energy density, we have seen the safety part, and we have seen the charging time. So these are like the good parts that we see from the solid state battery perspective. And a lot of industries are invested into it, and they're trying to develop this. But when I say solid state electrolyte, what does it mean? I've not mentioned any chemistry here. I've not mentioned what it is, because there's not just one solid electrolyte. There are many solid state electrolytes. When I was studying the literature for when I started the research into this, like there's a huge list of different types of solid electrolytes that have been there. But all of them, they can be broken down into like 3 different groups. You can say there are polymer based, oxide based, and sulfide based. And they have their own advantages and disadvantages, but none of the 3 you can see here are clearly the winners. Like all of them are lacking in some of the department. Okay, we're not going to go into each and every department because we're again too technical, but the key point here is, key takeaway is that whether it be an oxide-based electrolyte, it may be sulfide-based solid electrolyte, or a polymer-based one, they have their own advantages, but at the same time, they also have their challenges. They have their own disadvantages, which are yet to be overcome, or in some cases have been overcome, but yet to be commercialized or industrialized. So this is just a very broad classification, but this can be further classified. So can you move to the next slide? Yeah, so we can further classify them. You can broadly group them into crystalline, non-crystalline type of electrolytes. And again, even in both of them, we have inorganic and organic. So if we see into the non-crystalline ones, we have the organic ones, which are basically the polymers. And these polymers are basically solid polymers, can be gel polymers or composite polymers. Composite polymers is going to be basically like we have some polymer mixture and we're trying to mix it with some other compound. It could be an oxide based or sulfur-based one, and we are trying to soften it a little bit. Then we have some gel-based polymers, and then we have completely solid polymers as well. And then again, we also have an inorganic non-crystalline type, which is basically glass, like lithium-ion. And then we move to the ones which we are like having really which are really challenging one, but which are really promising as well. So the crystalline ones, the crystalline solid electrolytes, which are basically ceramic based ones, ceramic types. So it could be broken down to the one I mentioned before, the oxide based, sulfide based, and also phosphate based ones. And so what we're trying to do is we have these different types, and we're trying to study these different types, and we're trying to see which of them are suitable or which of them are giving us the best results. And even within them, when we try to see which particular chemistries are available, there are a lot of different chemistries, and I'm not mentioning any chemistry here right now because, like, once again, there are no clear winners. There's still a lot of research required, but there's also a lot of mixing going on. Like in my case, in my research, I had a oxide-based solid electrolyte, but it has its own challenges. So I was trying to use different polymers, and I was trying to mix them up. So basically, a composite study where I'm mixing polymers and oxide-based electrolytes. Can we move to the next slide? So we come to the challenges in solid-state batteries and why we have so many studies going on and why we don't have a clear winner yet. So we have different types of problems. We have different disadvantages or advantages for each and every types, and they can be broken down into different parts. And you'll find different ways of defining them as well. But one of the major problem we have is this interface problem, where with the part where the electrode is connected to the electrolyte, the line where it touches each other, basically. That's what we call as interface. And you can imagine this very easily, because if you have a liquid and you're putting liquid on a solid surface, the liquid has a very good contact with the solid because it's liquid, so it can seep into very small micro gaps which are not visible to our eyes. So the contact with the surface is like very good. But if you're touching two different solids together, and I believe if any of you guys are from mechanical, you would have known this, you would have studied this. The surfaces are having a lot of irregularities. Even if you see the surface like it's plain to a naked eye, it has a lot of surface irregularities. And when you're touching the two surfaces, they're never going to have a perfect contact between the two of them. There's always some small micro gaps, and then they're creating some problems. And that's basically an interface problem. And if we have this interface problem, this basically restricts a lot. This creates challenge when we are trying to transfer ions from one end to the other end, because the micro gaps that we cannot see are basically there, and they're not going to allow any transfer of ions from one point to another point. So that's basically increasing the resistance between the two objects. And the next slide is going to make you all very hungry, but it's just an analogy. So can we move to the next slide? So yeah, basically we have let's say an anode and cathode, and we have a solid electrolyte, and it's going to have a lot of surface irregularities. So I just tried to compare it with a burger, where when you're going to have this complete pack, sealed together, it's not going to have a perfect contact. And if I want to gel it together, then I'm going to use something. I'm going to add some sauce, and I'm going to add some mayo, and I'm going to add cheese, and I'm going to add some other compounds to make sure that it's gelled together. It blends in. It's not just like bread and patty and that's it. Okay. So this was basically a part of my research, because in my case, my solid electrolyte had a lot of interface problems. And so the reason why I was trying to mix it with polymer or trying to make composites with polymer is to ensure that the resistance is lowered as much as possible, and I'm getting a good contact between the two surfaces. So I was trying to improve the interference issues. So this is basically just an analogy to that how the interface problem is created for a cell, for a battery, and how we are trying to solve it in different ways. Can we move to the next slide? Yeah. So just in case the burger part was funny, this is just an actual photo where we can try to understand. So this is the anode part. This is the solid electrolyte in between. This is the cathode part. And if we zoom in to the sections, if we zoom to the micro sections, we can see the surfaces are irregular. And we can see here that there's going to be some resistance between the solid electrolyte and the anode part. There's going to be some resistance again between the solid electrolyte and the cathode. And this is the part which is very difficult for us to minimize. This is the part where we are trying to develop, we're trying to, and there's no thumb rule here. This is like an uncharted territory, and like everybody was trying different things until the last 2-3 years, and where they were trying to mix it with polymers, or they were trying to they're trying to add some liquid into the solid side just to make sure the contact is good, or maybe they're trying to apply pressure, they're trying to develop new sort of materials, anything that could basically improve the contact, and the studies are still going on. So basically, this is the interface challenge. That is one of the, from my perspective, it's one of the biggest challenge. But again, that is not the only challenge the solid state batteries have. Solid state batteries also have a lot of other challenges, where it could be the reaction with the air, with the stability. It could be the cycling, because we have seen that even though they're charging very fast, the number of cycles it has, that could be different. So possibly we could get some of the materials can give us up to 800 cycles on life cycle. Some of them could give 1,000, 2,000 as well, but it's a very challenging thing. And the current studies, it's like very difficult to reach to those levels. So they're trying to improve on that. One more difficult challenge here is that when we have that solid electrolyte and when we're trying to connect it with the anode and cathode, the repeatability of the successful cells that we're making. So how easily you're able to repeat the same cell without any changes, how good it is. It does, each and every cell is coming out with a good interface, or maybe some of them will have some defects, some of them will have some different failures. And how many of those failures are coming up? That's another problem. That's an industrialization problem. That's a manufacturing problem that's further troubling the solid state batteries. So there are a lot of positives on solid state batteries coming up, where we have very good energy densities, we have very good safety options, possibilities, we have very good charging times, and these three things alone makes it a very alluring technology to go ahead with. But it also has a lot of disadvantages, a lot of challenges that are yet to be overcome, that we have discussed so far. Can you go to the next slide? Yeah, so there are different companies which are working on these different challenges, and I've just named a few of them, but these are not the only companies which are working on solid state batteries. And a lot of big industries, a lot of big automotive makers, they have had joint ventures, or they have tie-ups, or they are funding these companies or the other companies which are coming up to develop these solid state batteries. One of them, like we are all familiar with, when the solid state battery comes up nowadays, everybody just remembers the name QuantumScape. So that's also got me interested into solid state battery. And so QuantumScape is, we're using something called as an anode-free lithium anode. So what does anode-free mean? It basically means that whenever we have a cathode material, like let's say the cathode material is made of nickel, manganese, cobalt. So we only know it's NMC, but it's actually lithium metal oxide. Basically, it's lithium, nickel, cobalt, manganese, and oxide. And we have that lithium on the cathode itself. So our cathode is basically having its own lithium. And when you charge the battery for the first time, when the cell is made and when you're charging it for the first time, this lithium, it's traveling from the cathode, it passes through the electrolyte and goes to the anode side. What QuantumScape mentioned in their presentation was that they have made it in such a way where they don't have any anode in the beginning. They only have cathode, and when they charge the battery, they have the cathode and they have the separator. That is basically their solid electrolyte. The lithium ion that's passing through the separator, and it's forming the anode. When the first charging cycle is made, the lithium metal is transferring and it's creating its own anode on the other side. And this is basically a very interesting concept, but at the same time, it's very difficult, because the way the anode is going to be formed, it should be uniform, and that's how QuantumScape manages it. It's something that we have been like, I have not been able to figure out, but it's again a very interesting concept on a lot of scales. When it comes to shipping batteries, when it comes to logistics of batteries, safety of batteries, this concept is very good. Then coming up to the other players, the solid energy, ionic, ion, or solid power, most of them they're using pure lithium metal as an anode, and some of them will be using silicon-based anodes as well. And coming to the electrolyte part, it could be an oxide-based electrolyte, it could be a sulfur-based electrolyte, it could be a polymer-based electrolyte. So you can see most of them are going to be some part of oxide or sulfide or polymer-based electrolyte. And it's gaining traction. It's coming up. There's a lot of things going on. And some of them have proven their own results. Like Solid Power has their cell. I think the cell was called Apollo or something, which had a very good energy density on it, about 110 ampere cell, and a very good overall performance characteristics that they were posting. SES again, they're also mentioned there, but I believe SES also uses liquid. Even QuantumScape uses some liquid in the cathode side, but it's not much. I'm not sure about Factorial. There's not much data available on them, but yeah, all of these companies and other companies have been working really well. And companies like Mercedes and Volkswagen, Ford, and all, they have tied up with some of these companies, and they're trying to develop, and they have mentioned targets to launch their electric vehicles with solid-state batteries as soon as 2026. Personally, I believe that's very ambitious targets for a lot of big automotive manufacturers, and this technology may still take this decade to develop. But in the next decade, we are definitely going to see a lot of competition coming to the solid-state battery and coming to the new battery technologies. Can we move to the next slide? Yeah, so as I mentioned, some of the major players like Toyota. Toyota has its own. Toyota, I believe, holds most amount of patents, if I'm not wrong, into the solid-state batteries. But Toyota personally has not made much progress into electric vehicles and solid-state batteries directly yet. They're still doing a lot of research in the background. Ford has recently have a tie-up with Solid Power. I have been working in Ford. I have worked in Ford for about 1.5 years. On EV design, but during that time it was not there. So just when I was leaving, I heard the news that yeah, Ford is having a tie-up with Solid Power, and it is very interesting to come up. Again, GM and BMW and again, Volkswagen, as I mentioned, has a tie-up with QuantumScape. Hyundai, I'm not sure. Daimler is having a tie-up with I don't know. But yeah, most of them, they're working with big players, and all of them have plans to launch solid state. Every big player is now like keeping one eye on the, except Tesla, because for Tesla is going really good with what they are having now. And Tesla is, I believe, interested into the dry electrode processing, which is very promising. As of now, they have really good sales volume, so they don't have any reason to like change. But at the same time, they are doing their own research on solid state batteries. This is me speaking on my personal level, because they have a really good research. They have a really good research lab, and the person who works or is a battery consultant for Tesla, I believe his name is Jeff Dan, is one of the pioneers, and everybody who knows about batteries or battery chemistries and into the battery world, they knows that guy as a celebrity there. So a very high level technological background they're having, and they're definitely going to continue working on solid state batteries eventually. So yeah, these are the players that are currently working. Can you go to the next slide? I believe that should be it. Yeah. So thank you.
Right. So thank you, Pranav, for your insights. It was really interesting to hear your opinion on solid state batteries. So as we are moving towards the end of the webinar, I would just like to refresh on the key takeaways from the session. So next slide, please. So what we learned and understood from this webinar is, first of all, transition is happening from conventional lithium-ion to new chemistries. So there are the technology is constantly evolving. Researchers and engineers are constantly exploring new chemistries beyond conventional lithium-ion batteries. And the transition involves several considerations, including improved performance, safety, cost effectiveness, and sustainability. Also, we understood about various upcoming technology trends, which includes increased energy density, faster charging, sustainability and recycling, silicon anodes, and second life batteries that are happening currently within the battery industry. Next, better performance than conventional lithium ion is what is being promised by these new type of battery chemistries. So these new battery technologies have the potential to offer higher energy density, faster charging, and longer life cycle compared to conventional lithium ion batteries. They are also cost effective. Some of these new battery technologies have the potential to simplify manufacturing processes compared to conventional lithium-ion batteries. The technologies can simplify production and reduce the number of production steps, which will eventually lead to cost savings and increased efficiency while manufacturing. We also looked into various emerging companies in the battery chemistry ecosystem. So there are several startups, several emerging companies which are constantly evolving and constantly experimenting with their product. So some of these leading companies includes Inolith, Next Tech Batteries, QuantumScapes, Scylla, Solid Power, and so on. Also, we looked at the various increased investment in electric vehicle batteries. So the growing demand for EVs and the need for advanced battery technologies to support this widespread adoption has led to this increased investment in EV battery technology by various players. And that is certainly a good sign for the industry that it's about to grow tremendously in the future. And lastly, the evolving end user needs and new EV models. So obviously, there is a need for longer driving ranges. There is a need to cancel out range anxiety and any fear of running out of battery power while driving. Also, there is a need for faster charging capabilities. So the introduction of these new technologies and the introduction of new EV models in the coming future with equipped with these technologies are best suited for these requirements and to address these type of end user needs. And this is what these battery technologies are being developed to cater to the evolving needs of these new EV users and the ever increasing EV adoption among the common public. So further, BIS research is upfront to tracking electric vehicles and battery related technologies and also share the insights with a wide range of industry participants. To discuss research product plans and recently launched titles by BIS Research, I would like to invite Komal. Over to you, Komal.
Thanks, Dhruva. So as you can see on screen, a lot of our research studies are focused on electric vehicle and battery technologies. So on the left side, you can see some of our recently published reports, such as immersion cooling fluids market for EVs, stationary energy storage market, sodium ion batteries market, and so on. And on the right side, you can see some of our upcoming reports and updates that are already in publishing phase, such as lithium-ion battery recycling market, next generation anode materials market, global cathode materials market, and so on. Now to discuss about the AI-based platform that we have, I'd like Dhruva Jyoti to take this up. Over to you, Dhruva.
Sure. The next slide, please. Yeah. So our proprietary platform, Insight Monk, is a one-step solution for customers looking for syndicated reports, company profiles, expert insights, key player data, market statistics, expert consultation, and any type of noise-free search on deep tech topics, and a lot more. It offers a large set of relevant data curated by our internal and network experts and is readily available for access as per the bespoke needs. Insight Navigator is also another product, which is a market intelligence assistant for Insight Monk, again by BIS Research, which specializes in deep tech technologies. It provides insights and data on various themes such as healthcare, advanced materials and chemicals, aerospace and defense, agriculture and food tech, automotive, electronics, and semiconductor, energy and sustainability, and so on. So that was the brief about our internal platform, that is Insight Monk and Insight Navigator. So yeah, over to you, Komal.
Okay, thanks, Ruba. So, with this thought, let's just conclude today's session. And now I declare the forum open for any questions. So, I request all the listeners to kindly type in the question, and I will be happy to pass the question to the esteemed speakers. So, I believe we have our first question, and the question is for Vani. And the question is, with the growth in EVs expected over the coming years and production capacities limited by the current mines expected to be reached within the next 3 to 4 years, are there plans to address the looming supply crunch?
Very, very good question. Let me share some details about where lithium production levels are today and where they're heading. The top three countries for lithium production are Chile, Australia, and China. I have 2021 numbers for lithium. Chile produced 20,000 tons. Both Australia and China produced 14,000 tons each. The 2022 numbers are not out yet. US produced in 2021 only 900 tons. In 2024, US is expected to be number 2 producer in the world, thanks to Tesla. The production capacity of US for lithium will go up by 15,000 tons. So US is supposed to hit close to 17,000 tons per year lithium volume by end of 2024. However, the global lithium usage at the current rate will consume the complete lithium supplies we have by 2045 to 2050. You understand what I'm saying, right? That means without the discovery of additional lithium resources, the current lithium mines will run out of lithium before 2050. Two things to actually, there are three ways you can mitigate it. Obviously, we're going to be looking for new lithium mines. I know, India has discovered lithium in Jammu and Kashmir. So there are a lot of other areas people are exploring. And you have to develop the recycling technologies to recycle lithium also. Not very many companies are recycling lithium today. It needs to be developed actively. And cobalt and nickel, it's even worse. We're already designing cobalt out completely, and nickel needs to be designed out too. The third thing is other technologies other than lithium. I expect the utility-based energy storage systems to switch to sodium very rapidly. While the energy density of sodium technology, sodium-ion batteries, is not as high as lithium-ion, the life data looks excellent. And so stationary applications, we don't worry about footprint and weight. So if you're going to be using brand new batteries for your storage applications, we're going to be branching out. The second thing is we need to learn to repurpose automotive lithium-ion battery packs, because the specification calls for an automotive battery being a failure once the residual capacity drops to 80% of the original capacity. But that number is different for stationary applications. The residual capacity needs to drop to 50% of the original capacity before it is declared a failure in a stationary application. That means we need to recycle the automotive battery packs first by disassembling them and reassembling them back into stationary battery packs by extending the life, and then learn to recycle all the materials. I do work with an Indian recycling company called Loham Cleantech. And Loham, they're recycling lithium today. They're one of the very few companies I know that is recycling lithium. So which is very, admirable. So these are all the things that we have to look at. So we can extend the life of the current batteries. We can reduce the usage of the raw materials, so we can extend the availability of the raw materials. And we also need to diversify and find out different chemistries. So these are all the ways that one needs to look at in order to move to what I would call future technologies and what we expect to happen in future. And the last but not the least is we're all worried about rechargeability and infrastructure. More than that, we need to have to me, an EV charging system, EV charger, it's just a faucet. Somebody needs to supply water to that faucet. Even in the US, where we worry so much about our power supply, this past summer, California issued warnings to customers not to charge EVs when it got too hot. Can you imagine what happens in India? We don't have parking garages in India. So most of the vehicles are parked on the street. So how are you going to charge your cars? Does the country have enough generation capacity to supply power to all the chargers? We don't have that capacity in the US. If a neighborhood has more than 15% to 20% EVs, the transformer that supplies power to that neighborhood will run out of capacity. The T&D lines will run out of capacity. Nobody's talking about it. We need to have massive how do I say this? More T&D lines and more transformers and more generation capacity to address these variations in consumption. So all these are all massive challenges, a lot of opportunities for entrepreneurial minds to solve these problems. I hope I answered I posed more questions, I believe, than what I answered, but I want all of us to start thinking about these. Thank you.
Thanks, Wani. So now I believe we have our next question, and this question is for Pranav. So the question is, when it comes to the commercialization and industrialization of solid state batteries, what is your opinion on the complexity of replacing the production line for conventional lithium-ion batteries with the one of solid state batteries? Also, do you think that it is possible to make cylindrical type solid state batteries?
That's a very interesting question. For the first question, it depends definitely if how the process, what particular type of solid state we are using. For example, if you're using a polymer-based solid state electrolyte, it's definitely possible to use the same one. But when it comes to oxide-based ones, it's slightly different because we need an additional processing step. We need higher temperatures when the particular electrolyte is getting developed, or it's getting when the process of batteries getting to them. So we need the cost of the initial cost of setting up will definitely increase in the situation. As for the cylindrical cell, this again depends on how flexible your solid state electrolyte is. It's not going to be feasible in the first stages of solid state batteries to have a flexible enough solid state battery to have a nice stored cylindrical cell. But it's not necessary that we need or we have to have a cylindrical cell as a form factor for solid state batteries, because the prismatic form factor provides a very good packaging efficiency when it comes to packaging. And if we are not having any thermal restrictions, like in case of solid, possibly, then I would say having a cylindrical cell doesn't really help, because it's just using up an additional space and reducing your overall volumetric energy density. So having prismatic would be a better option there. But definitely on the production scale, we see that it's challenge of using the current production system. We need to have at least 1 or 2 additional stations where some processing have to be added.
Perfect. Thanks, Pranav. So I believe since we are running out of time, so any unanswered question will be answered with the help of speakers, and we'll answer these questions and send it across via email or blog post. So let's conclude the session. And thank you everyone for attending today's webinar. And thank you very much, speakers.
Thank you.
Thank you.
Yeah, so nice to meet you. Everybody have a good day. Bye-bye.
Have a good day. Bye-bye. Thank you.